Swayam Prabha. Digital India. Educated India.
So, welcome back. We were talking about chemical thermodynamics. Okay. So, welcome back. We were talking about chemical thermodynamics in last class, that is where we left, and we were talking about reviews of different why it was needed to understand chemical thermodynamics and why that the products we need to understand the composition and temperature of the products which are in a state of chemical equilibrium, and that in a combustor the design target is to ensure that the fuel and air have sufficient residence time to mix and react and attain thermodynamic equilibrium. And often chemical equilibrium, as we have seen, gives us good engineering parameters, as the total heat release, the total power output, these sort of things, which are the first most important parameters that you need before you design an engine. And then we talked about practical reactance, stoichiometry and postulates, and we derived the Gibbs free energy, the equilibrium condition in terms of Gibbs free energy, the criteria for chemical equilibrium, element conservation, and then we obtained the chemical potential, and we derived the equilibrium constant Kpt, which is given by this formula. Okay. And of course, there is also a Kc, that is equilibrium constant in terms of concentrations, and we showed that how we do not need to tabulate the equilibrium constant for individual reactions, but we can obtain it from the formation. If we write a hypothetical reaction by which a species is formed by a given reaction, and we can write the equilibrium constant for a given reaction in terms of the equilibrium constant of those reactions that form the given species involved in the present reaction. Okay. So, and of course, the most important thing to note is that as you have seen that this equilibrium constant, this is essentially this is our equilibrium constant definition, and this is given by the product, the continued product of the partial pressures of a given species raised to their the difference of their stoichiometric factors, right, the stoichiometric constants that are being involved. So, this is the definition, and now as we have also shown the importance of equilibrium constant when you have when you involve more species which are invariably present in the equilibrium, in the chemical equilibrium in the equilibrium situation of the products, then you can get away for fuel lean mixtures for phi less than 1. But for phi greater than 1 for rich mixtures in which you have more species formed, especially carbon monoxide and hydrogen, and then you need the equilibrium constant of additional reactions, which is the water gas shift reaction, to give you all the equilibrium composition essentially. But then the next important thing is that how do you obtain the temperature, and for that we need to introduce few concepts which are called heat of formation and sensible heat. So, heat of formation, the heat of formation is a very important concept. The heat of formation is defined as the heat required to form 1 mole of reactants from its elements. Remember, reactants need not be elements, reactants are essentially in molecules, right. Methane CH4 is formed from C and hydrogen, carbon and hydrogen. Hydrogen molecule itself is formed from 2 atoms of hydrogen, so on and so forth. So, the heat of formation is essentially the heat required to form 1 mole of reactants from its elements in their standard state, either at constant volume, which involves the internal energy. Note the change in the notation here, we are denoting the specific internal energy by small ei, or at constant pressure, in which we are mentioning it as enthalpy at a reference temperature T0. Okay. So, the heat required to form 1 mole of reactants from its elements in their standard state, either at constant volume or at constant pressure at a given reference temperature T0. Okay. So, this is the heat of formation. So, as an example, if you are interested in the heat of formation of CO2 or rather the heat of formation, this is essentially not CO2, this is heat of formation of rather CO, which is formed from 1 mole of carbon, solid carbon, graphite, and half mole of oxygen, and that gives you 1 mole of carbon monoxide. Okay. And then its heat of formation at the standard temperature, at the standard reference temperature of 298.15 Kelvin is minus 26.42 kcal per mole of CO. Okay. So, that is the heat of formation of CO. Okay. Now, it is important to note that the elements do not, by definition, the heat of formation of elements is equal to 0. Okay. Only molecules have heat of formation. Okay. Now, what is sensible heat? This is the heat of formation. Essentially, it is the energy, you can think of it like the energy that is stored in the chemical bonds. Okay. That is the heat of formation. What is sensible heat? Sensible heat is the energy that is required to raise the temperature of a substance from T0, that is the reference state, to T. Okay. So, then the amount of energy is essentially the energy sensible heat for CO at a temperature of say 1000 Kelvin is equal to the amount of heat required to raise the energy is required to raise the temperature of CO from 298.15 Kelvin to 1000 Kelvin. And of course, you are right that to estimate that we need to know the specific heat capacities, and that is where the CPs come in. Okay. So, this is called that is where the CPs come, which are actually functions of temperature, the specific heat. So, now we can define what is the heat of reaction. Now, the heat of reaction, this is a very important concept. Now, we must also distinguish and never get confused between the heat of formation and the heat of reaction. By definition, the heat of formation is a property of a given molecule. Okay. It is a property of a species. Heat of reaction is a property of a reaction. Okay. So, that is the basic difference. So, what is that? The heat of reaction at a constant pressure for a general reaction of this form, as we have defined, this is the general reaction, is given by, this is the heat of reaction, is given by the heat of formation of the products minus the heat of formation of the reactants. Okay. That is the heat of reaction, okay, which is clearly given in a generalized form by this equation. Now, suppose a reaction is exothermic, it releases heat. The question is, will the heat of formation be positive or negative? Now, if it releases heat, okay, the heat of formation, the heat of formation of the products, which is the property of the product, will definitely be less than the heat of formation of the reactants, because the reactants have given up this heat, released this heat, which the products did not have, right. Now, the products can be heated because the products have been heated by this heat of formation of the reactants, right. You see the point? That is, the reactant, suppose you consider the methane air combustion reaction, CH for O2 goes to CO2 plus water. Now, yes, our common sense suggests that under normal conditions, if you do combustion at constant pressure, your CO2 and water will be at high temperature, and of course, your COH4 and oxygen was at low temperature. Okay. Now, but then you need to see why is the CO2 and water at high temperature. It is at high temperature because these had CH4 had large heat of formation, which it has given up, by the combustion reaction, and this heat of formation has now been absorbed by the CO2 and water in form of a sensible heat, which has raised its temperature. Okay. But you must know that the heat of formation of these quantities is less, okay, and that is why the reaction is exothermic. So, for an exothermic reaction, your heat of reaction is less than 0, and for an endothermic reaction your heat of reaction is greater than 0, because your endothermic reaction means the heat has been absorbed. Now, once the heat has been absorbed, where does it go? So, the products has absorbed the heat, okay, to increase its own heat of formation. So, the heat of formation of in an endothermic reaction, the heat of formation of the products is higher than the heat of formation of the reactants, and that is why the heat of reaction is greater than 0 for the endothermic reaction, whereas for an exothermic reaction the heat of reaction is less than 0. Okay. So, heat of reaction is defined for any generalized reaction, whereas the heat of combustion at constant pressure is defined as the amount of heat released when 1 mole of fuel in its standard state is completely reacted with oxygen to form water, carbon dioxide and nitrogen if there is fuel bound nitrogen. We do not need to worry about this, these are typically for different kind of propellants and etc. Okay. Now, of course, there is one thing here, that is when you form water, water can be in gaseous state, it can be in liquid state. So, depending on that you can have a higher heating value or lower heating value. Now, you can also define, I will just quickly go over this derivation, that you can also obtain the heat of reaction from KPT, that is when you define this the standards, the specific chemical potential can be shown to be equal to the specific Gibbs free energy, and which is given by this form, and then of course, this is our relationship for the equilibrium constant, and we can basically write, we can take basically here this on this side, and then we differentiate with T, and once we differentiate with T at constant pressure, we will see that this the derivatives of dHi and dSi will drop out and only this will remain, and this is what we will get, and it can be shown that your Kp, this R0 times d ln Kpt divided by d 1 by T is essentially is equal to your minus of heat of formation of products minus heat of formation of reactants, which is the heat of reaction, negative of the heat of reaction. Okay. So, that is how you can obtain this. Now, how do you obtain adiabatic flame temperature from energy conservation? Okay. Adiabatic flame temperature is the temperature which we will see is essentially the temperature of the equilibrium products. Okay. Now, the total enthalpy, this is a very important definition. The total enthalpy at a given temperature T per mole for an ith species. Ith species mean can be anything, it can be methane, oxygen, water, CO2, etc., is essentially sum of two things, the enthalpy of formation and the sensible enthalpy. That is, you can think of it like this, it is the inherent energy that it had because of its different kinds of bonds, and the energy that has been absorbed in the bonds because it has been raised from the standard state to a higher temperature state. Okay. So, the total enthalpy is a sum of these things. Now, of course, you see in a when you have a suppose a combustion happening at constant pressure inside a vessel, now the vessel walls can be sealed. Okay. So, there is no heat that is crossing the this control volume boundaries or a system boundaries. So, essentially it is energy from the chemical bonds becoming sensible enthalpy or vice versa. Okay. There is no external energy coming from anywhere, you must remember this thing. Okay. So, it is essentially rearrangement of the enthalpy between the enthalpy of formation and the sensible enthalpy that is happening in combustion. So, please understand this thing, in combustion, when you model combustion in a given engine or something, there is no, it is not that, it is not like this. Okay. There is no energy, you cannot model it like an energy crossing the system boundaries. It is basically rearrangement of the enthalpy from the heat of formation to the sensible part, sensible enthalpy part. Okay. So, if there is no energy coming in, okay, so then how do we model this? How do we write this? We can write that the total energy of the reactants, this can be, this thing is essentially summation Ni Hi Ti at T0 and with respect to T0 is the total enthalpy of reactants, which is equal to total enthalpy of products. Okay. Since of course, since there is no additional energy coming in, the enthalpy of reactants is equal to enthalpy of products. Okay. And then we can put the enthalpy of formation on one side and the sensible enthalpy on the other side. Okay. So, now what we have essentially done is that, so this is the total enthalpy, right. This is the total enthalpy of the reactants, this is the total enthalpy of the products. So, you can use this one to substitute here and substitute here. So, once you have, then you have basically on the left hand side you have the enthalpy of formation of the reactants plus sensible enthalpy of the reactants, and you have enthalpy of formation of the products plus the sensible enthalpy of the products. Okay. Now, what we have done in this step is essentially we have collected the enthalpy of formation of the reactants and the products on the left hand side, and we have collected the enthalpy, the sensible enthalpy of the reactants and the products on the right hand side. Okay. Now, what has happened is that the enthalpy of the, if this is a combustion reaction, say the enthalpy of the reactants, the enthalpy of formation of the reactants is much high. Okay. And that when it has been released, it has been converted to sensible enthalpy of the products. So, as a result of this, because the sensible enthalpy of the products has been increased, it has been increased because its temperature has increased. So, this T2 is the temperature at which this sensible enthalpy can be realized, and hence T2 is called the adiabatic flame temperature. Okay. So, you see the thing, that is the, you have the reactants have lot of enthalpy of formation, whereas the, it does not have to, it did not have too much sensible enthalpy because it can be at a reference state itself, whereas the products have small enthalpy of formation, but it has very large sensible enthalpy. The very large sensible enthalpy is the enthalpy is large because it is a function of temperature, and that temperature which it has been raised, which this sensible enthalpy has been realized, is called the adiabatic flame temperature. So, of course, you see this is not an explicit equation. Okay. This is still an implicit equation, and we have to do some iterations to essentially find the enthalpy of the adiabatic flame temperature. But essentially the adiabatic flame temperature comes purely from the energy conservation, that is or rather it comes from the rearrangement of enthalpy between the sensible enthalpy and the enthalpy of formation. Okay. So, it can be also thought of, I mean formally it is defined like this: adiabatic flame temperature, that is, if you have a given uniform mixture with an initial temperature and composition is made to approach the chemical equilibrium through an adiabatic isobaric process. Adiabatic process because there is no heat entering into the control valve, into the system that I was talking about. Isobaric means constant pressure, okay, at a pressure P, then the final temperature is the adiabatic flame temperature Tad. Why is Tad higher than the normal temperature? That is, it is a very basic question, right. It is almost an obvious question that I am asking, that why is the temperature of the products higher than the temperature of the reactants? Because the reactants had once again very large enthalpy of formation. Now, because of the chemical reaction, that enthalpy of formation is now converted into the sensible enthalpy of the products. Now, the sensible enthalpy is of course a function of temperature, and because the sensible enthalpy is very high, the temperature must be high, okay, and as a result of this, the adiabatic flame temperature in which this sensible enthalpy is realized is large. Okay. So, that is why when you have combustion, you basically have large final product temperature is high. Now, you can also think of it like this, that in this enthalpy temperature diagram. So, suppose this is the reactant. So, first it can be, it essentially goes from, this is the 1 is the reactant state, 2 is the product state. It essentially goes like this, but we can think that it involves like 3 steps. So, first it goes to the T0, that is the reference state, okay, the products, the reactant, sorry. So, this is the reactant. So, it goes to this reference state and then it releases the energy. Okay. So, as it energy releases, its enthalpy goes down, the reactant's enthalpy goes down, but then now that energy, that chemical energy that has been released is essentially taken up by the products, and then it becomes hot because now it has absorbed all the enthalpy that is released by the reactants, and now the sensible enthalpy of the products has increased, and hence this T2 is equal to Tad is greater than 1, is greater than T1. Okay. So, please remember this, that there is no additional energy coming from anywhere else. It is a chemical energy that is converted into sensible energy, sensible enthalpy, okay, and that energy conservation on the left, on the between the reactants and the products, gives you the adiabatic flame temperature. Okay. Now, what does adiabatic flame temperature depend on? Now, one of the most important parameters in combustion is adiabatic flame temperature. Okay. We do combustion because we want the temperature to be high. Once the temperature is high, you can if you can, as you remember from a thermodynamic cycle, if you have heat release at high pressure, if you have a system which is at high pressure and at high temperature, you can extract work out of it. Okay. So, it is because of this high adiabatic flame temperature that is combustion is attractive, and that is why you have combustion in engines. Okay. Now, so it is very important and to understand that why, on what are the parameters on which adiabatic flame temperature depend on. Of course, it depends on the equivalence ratio Phi, which is the actual fuel air ratio divided by the stoichiometric fuel air ratio, and it also depends on the CH ratio, that is the carbon to hydrogen ratio, though that is less dominant. So, this is how the adiabatic flame temperature for different fuels look like. So, this is, you see, methane, propane, benzene, ethylene, hydrogen, carbon monoxide and acetylene. Okay. And you see that its peaks at almost at equivalence ratio peaks at equivalence ratio of 1, though it is slightly shifted from 1, but all the temperatures you see are around this 2200 to 2600 Kelvin, when, because this is adiabatic flame temperature in air. Now, one more important thing is that to note is that the adiabatic flame temperature, you know, if you have the adiabatic flame temperature is also depend on the medium in which you are burning. If you are burning in pure oxygen, your adiabatic flame temperature will be much higher than if you are burning in air. The reason is that the adiabatic flame temperature, as you see, is essentially comes from the sensible enthalpy. Now, if you have lot of nitrogen, nitrogen is not participating in the reactions. So, a lot of the sensible enthalpy goes in heating up the nitrogen also. So, the adiabatic flame temperature in air which contains nitrogen for a hydrocarbon combustion reaction is definitely lower than that of the adiabatic flame temperature in pure oxygen. Okay. Anyways, so this is the adiabatic flame temperature in air. and this is the range in which it is in which you have the adiabatic flame temperatures. So, of course, you see the most important thing is that on both sides of the it is low on both sides of the equivalence ratio, okay, and it is this peak type behavior we see. Now, of course, if equivalence ratio is less than 1, if burning is lean, you do not have, you have a less supply of fuel. Of course, if you do not supply the given amount of fuel, you do not achieve that kind of temperature. So, it is obvious, but why is the adiabatic flame temperature low when you have fuel rich combustion also? Because you see now the lot of the energy of the sensible enthalpy is now spent in heating up the unburned fuel. Of course, you do not have unburned fuel as such, but you have carbon monoxide and hydrogen. So, a lot of the energy, which is also a fuel actually. So, a lot of the energy is now spent in heating up carbon monoxide and hydrogen when you have fuel rich combustion, as we have seen in the equilibrium composition calculation. And so on the adiabatic flame temperature basically goes down on both sides of stoichiometric condition, right. So, the next parameters are that it depends on CH ratio, because you see it depends on whether it is methane, propane, benzene, ethylene or acetylene. Of course, it is very clearly seen that acetylene has a much higher temperature than methane. Okay. The reason is that you see acetylene has a triple bond, okay, whereas methane has a single bond. So, when you have triple bonds, the bond energy is essentially high, but at the same time acetylene can contain less hydrogen than what methane can contain. So, it is that is a reducing factor, but on the other hand, because it has got less hydrogen, it demands less oxygen for water formation. Hence, if the requirement of oxygen is less, you will need less nitrogen also, and nitrogen is basically you are just wasting energy in heating up the nitrogen, right. So, these are the factors that determines the CH ratio, bond energy, less hydrogen or more hydrogen, and the demand of oxygen essentially determines the adiabatic flame temperature. Now, finally, you see that there is an asymmetry in shape also. The adiabatic flame temperature, this side is much smooth, whereas this side is much steep, right. Now, that has to do with the definition of equivalence ratio, and if you define the normalized equivalence ratio, you will find that this is reasonably more symmetric. Of course, you must also note that there is a lot of soot if you burn in fuel rich, because of the unburned hydrocarbons and particles that are being formed, and this CO, there is some ring formation, ring structure formation, and then there is polymerization, and then you form soot, and but that is why fuel rich combustion is very much unwanted. And then there is a most important, very important phenomena of the rich shifting of the maxima. What is that? You see, intuition suggests that yes, we understand why adiabatic flame temperature should peak at stoichiometry, but you see that it is not exactly peaking at stoichiometry. Stoichiometry is here, whereas this is peaking here, 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 and this is peaking here. Why? Okay. This is a very important question to answer, and this has to do with essentially the equilibrium, chemical equilibrium. Okay. The reason is that you must know that these products are not in a frozen state. If they were in a frozen state, you will find that the adiabatic flame temperature peaks at phi equal to 1. But because they are in a equilibrium state, the CO2 and the water that is being formed, they basically dissociate, that is the CO2 becomes CO and oxygen, and water also decomposes into hydrogen and oxygen. There is also continuous dissociation, albeit in small amount, that is going on. Okay. Now, these dissociation reactions need some energy, okay, and it turns out, it can be shown that the dissociation reactions are stronger, that is, there is preferential dissociation on the lean side. There is more dissociation going on the lean side, both for CO2 and water, than you have the dissociation on the rich side. So, if you have more dissociation on the lean side, there is more requirement of the energy that was released. Some part of it is basically sucked back to form, to basically do this dissociation reactions, and this sucking back of energy happens more on the lean side than on the rich side. So, as a result of this energy that is being reabsorbed because of the dissociation, your adiabatic flame temperature shifts to the rich side, and you do not have the adiabatic flame temperature maximum on the at equivalence ratio of 1. Now, this is very important, and this factor needs to be noted if you are designing a combustion combustor, a standard combustor. Of course, you will see that later this adiabatic flame temperature also determines the pollutants being that will be emitted, and presently everybody wants to basically work on this regime, so that the temperature can be less, there can be no soot, there can be no carbon monoxide formation, and but of course there are other challenges that are associated with this, we will talk later. But once again, coming back to the dissociation, you will see that with increasing pressure, okay, you will see that with increasing pressure this basically this adiabatic flame temperature becomes more and more peak towards the stoichiometry. So, this at a higher pressure, this would what the this is what the adiabatic flame temperature graph for methane would look like. Okay, it would shift more towards equivalence ratio of 1. This is because the dissociation reactions are diminishes. The intensity of the dissociation reactions diminishes at high pressure, as a result of which the adiabatic flame temperature tends to shift back. And as a result of this, once the dissociation reactions are diminished, your the energy that is consumed in this dissociation reaction is also diminished, and as a result of which the adiabatic flame temperature increases with pressure at a stoichiometric condition. And this is what you see, that as pressure increases, the adiabatic flame temperature becomes higher, and the peak shift backs towards 1, because the pressure serves to reduce the extent of dissociation of CO2 and water, and in doing so force the reaction towards better completion. Okay. So, with that we would end this first module of review of chemical thermodynamics, where we have obtained Kp, the equilibrium constant, where we have obtained the concepts of enthalpy of formation, the heat of formation, the heat of reaction. We have obtained the concept of adiabatic flame temperature, and the very important concept of why the adiabatic flame temperature shifts on the rich side, rather it does not peak at equivalence ratio of 1. So, thank you very much for your attention, and we will meet again, and when we meet again we will discuss chemical kinetics. Thank you.